sine theta equals plus or minus lambda over a. Does that work? Note that instead of dividing this into upper and lower, if I divided this into 4 parts, then I could do the same thing, except that now the cancellation occurs with partners that are half as far away as before. And so in that case, if we divide the slit into 4 parts instead of 2, then we get that sine of theta would need to equal plus or minus 2 lambda over a. And we could continue on with this if I divided it into 6 parts. It would be plus or minus 3 lambda over a. The end result winds up being that theta dark goes as m lambda over a, where m can be plus or minus 1, plus or minus 2, plus or minus 3, so on and so forth. Yay? And so
Professor,
yeah.
to make sure that is 2 lambda over a.
If we had divided this, instead of putting the dashed line here, if I had made it into 4 parts, so 1, 2, 3, 4, then I could cancel here and cancel here. And then I get sine theta dark is going to be plus or minus 2 lambda over a.
Okay, I'm just making sure that it is actually a, because from how I see it, it looks like a 9.
It's an a.
I'm just making sure.
Understood. If I had divided this in 6 parts instead, it would be sine theta dark is plus or minus 3 lambda over a, and so on and so forth. So really, you could start to wonder whether or not kind of the intensity pattern of our double slit, part of what we're seeing is the ideal carrier envelope with the diffraction through the slit. Bless you. Yay? Okay, so let's jump back far enough that and I promise we'll come back and we'll do more stuff with this than you're really going to want to do. In fact, I think I already warned you that I have an unhealthy fixation with the workings of the human eye. So, any of you have your driver's license? I can't gauge stuff like that. Yeah, a few of you. Okay, so one of the things that they make you do is they make you take an eye test.
Oh yeah, I
Right.
did.
So
That's anyway.
do they care that you know that that's an H? That's an H, by the way.
They don't care. No.
They don't. What are they checking?
They check left and right.
And you can see the
E, M. I forgot. I think H and E.
They're checking compared to what the average person can see at 20 feet. They're checking your resolution limit. You put 2 lines or dots adjacent to each other. At what distance can you not see that there are actually 2 objects there? And what they're comparing is your eye to the average healthy 20 eye, what the average eye can see at 20 feet. Right? Can you see at 20 feet what the average healthy eye can see at 20 feet? Without my glasses, y'all disappear. So I can't pass that test without corrective eyewear. But
God bless you.
that's hard. So why is there any limit whatsoever? Well, on some level, your eye is a slit. It's not a vertical or a horizontal slit, it's a circular aperture. But there's a fundamental resolution to how close you can put adjacent objects without them looking like one object based on the size of the aperture of your eye. Right?
What part of your eye is that?
The pupil, the part that lets light in.
The iris?
So the iris, yeah, the iris is the colored region around the middle of your eye. Light doesn't actually pass through the iris, but the iris is like a set of curtains that opens and closes depending on the ambient light.
How's the retina?
The retina is the target, so you're trying to pass light onto the retina. So the opening of the iris is the pupil, and so
What's the black part in the center called?
the pupil.
Okay.
And it's only black because it's a net absorber, right?
Yeah.
Light comes in, but it doesn't come out very well.
But somebody's eye is not black, it's like blue, gray.
Around the edge or at the center? If their eye is blue or green at the center, then they can't see.
Center, the pupil's always black.
barring you know what, I'm on video, so it should be. So all that's to say is the size of that is what sets the diffraction limit. So it have you ever, we don't really live in a rural area, but have you ever been standing on a road watching a car in the distance approach you?
Mm-hmm.
Yeah.
At night? At night, if it's far enough away, their two headlights may look like just one headlight.
Mm-hmm.
When it gets close enough to you, you can actually resolve that there are two headlights.
Yeah.
What you have just discovered is what is the diffraction limit of the circular aperture of your eye. So that's how you can gauge what the diffraction limit of your eye is. By the way, it's also related to how small I can make this from a given distance and you not be able to tell it's an H. So it's not a very good measure of your eye health, but it's the one we use because it's cheap. So, all right, we'll come back and talk about the human eye because, unfortunately for you, you're stuck with me. But this is the origin of your DMV eye test. If we take a string and we glue it to the wall, one side of it, if we send a pulse down the length of the string, some of it is going to reflect back off of the wall. when it reflects, what's the orientation of the pulse? It's inverted, right? Yay? The optical, so it's gone from an area where the wave can move quite easily to a region where the wave doesn't move very well, right? The medium can't really respond. The optical equivalent of this is what happens when it reflects off of a surface where N2 is greater than N1. Okay? If instead, and I apologize for my total inability to draw, as you know well enough by now, I have tried to rectify this. I even took art classes.
The water is too slippery.
If we tied a string to a ring and looped the ring around a smooth bar, when this reflects, what's the orientation of the pulse? Still positive. Because this time it can drag the ring up. Yeah? The optical equivalent of this is when it reflects off of, I use this I think. Off of the boundary between N1 and N2, where N2 is less than N1. Yay? So, let's look at interference in thin films. Does anyone wear glasses for reasons other than fashion? Yeah?
The light blocker.
So I just got these. I know they look like the last pair that I had.
Oh, really?
They're slightly different. I actually wanted the same pair, but they don't sell those anymore. This has like a little change, right? That was difficult for me to accept. I don't like change. But one of the things that they sold me is this has an anti-glare coating. It also has a blue light diminishing feature. I gotta tell you, I made it through half a century without that. And I haven't really noticed any benefit of this other than the fact that when something is like behind me flashing lights, which because I'm a bad driver, people flash their lights at me a lot. I get a flash of blue light reflected back off of my glasses at my eyes, which I don't appreciate. So
The other thing is blue light's an endocrine disruptor.
I sleep like 4 to 6 hours a night as it is. So what's it going to do to me that? When you're an old man, when you're an old person, I don't want to assume anything here. When you guys are old like I am, when you people are old like I am, I'm trying to be better. I am trying to learn. But when you people are old like I am, hopefully you're not as achy as I am, but you'll still be achy. And it will be tough to stay asleep for more than, I don't know, 4 or 5 hours at a time. I just can't lay down that long. Hurts my back. But blue light blocker, I have to admit I was intrigued because I do like the idea of interference in thin films. So let's see how this works. So we're going to assume near normal instance. And we're going to say that lambda n is just lambda over n. So lambda would be the wavelength in vacuum or basically in air, since the index of air is basically 1. So when a wave traveling from a medium of index of refraction and 1 towards a medium of index of refraction and 2 it'll undergo a 180-degree or pi phase change if n2 is greater than n1. It'll undergo no phase change if n2 is less than n1. And this is only upon reflection, not refraction. Yay? So, bless you. So, let's look at you ever seen a soap bubble? And if not, wash your own dishes.
I say no.
But if you've seen a soap bubble, you probably have seen that under white light, you see kind of like a colorful pattern off of the reflection on the bubbles. This is why. So we are going to have air, some film, and some air. Right, so this could be the water, the soap water mixture that the bubble's made out of. Outside, there's air. Inside the bubble, there's air. Yeah?
What would be the film made of?
This could be water, right?
Water?
It could be glass. It could be
Like in the soap bubble, what would be the?
water.
Water.
Very, very, very tiny little bit of soap. So so do you guys understand what I mean when I say near normal instance? What I mean is that it's doing this, right? I'm not going to draw that because it puts these lines too close together to actually understand what's going on. And so I'm going to greatly stretch this out so that we can actually see the ray instant and reflected and separated. So yay. But some of it is transmitted. So that should be parallel with that. It roughly is. Some of this gets reflected. Wind up parallel to this. Some of this gets reflected. Okay, so instant ray. So let's call this, I don't know, I didn't name them, but oh well. 1, 2, 3, and 4. What's the phase shift of ray 1 from reflection? Assuming that the film has an n greater than that of 1. Right, which it kind of has to.
So the film will be or N2?
Yep. And assume that the film has a higher index than air.
It will be 180?
Uh-huh. What about ray 2?
No phase change
No phase change. Why not?
because one is less than N2, or the N of air.
Yep.
Why not?
They're parallel.
So when it reflects, it's reflecting off of air. The film has a higher index than air. Yay?
So that makes it zero phase change?
Yep. Our rules are it undergoes no phase change if N2 is less than N1. Yay? What about for ray 3? What's the phase change?
Is it 180?
0?
It's 0. Why?
Same reason.
I'd go one further. I'd say that ray 3 never reflected. It only refracted, right?
Yeah, it
Refraction doesn't give you any phase shift.
goes- oh, you're going to the way.
What about ray 4?
Zero.
It also would be 0?
Why is it 0?
Because we have two
It's
opposite
not
180 degree
reflect at
shifts.
all.
Nope.
It's going
Because
into
it
air.
doesn't reflect.
It reflects here, right? So this is a refraction, but it reflects here, but it's reflecting off of a lower medium. Then it reflects here, but again, it's reflecting off of a lower medium. Then it refracts. So
Right. Watching that last step, it doesn't reflect. Or would it, no, it would reflect, wait. No, I don't know. No.
So ray 4 underwent 2 reflections, right? One here and one here, but neither of them were in media that had a higher index than the one it was already in. Ray 1 only undergoes 1 reflection, and it's off of a medium that's higher than the one it's already in. So how much extra travel did ray 2 do than ray 1? Assuming near normal instance, and we'll let this distance be t, the thickness of the film.
T, right? 'Cause
2t,
2T because it went down then up.
down then back up. So there is, if we put our observer here, right? If our observer wants to see constructive or destructive interference, this is determined by a couple of things. One, by reflections, they're 180 degrees out of phase. So in order to bring them in phase, what does 2t have to equal? So if we want constructive interference,
Has to be an entire wavelength, correct?
or at least a multiple of it, what do we need? Well, we need it's half a wave out of phase here, right, by reflection. And so 2t is going to have to equal half a wavelength. Yay? But it's half a wavelength in this new medium. And so our constructive interference is going to occur if 2t is m plus half times lambda n. But remember that lambda n is lambda over n. And so we need 2nt is m plus half lambda. What if we want destructive interference? Well, these two are already out of phase, right? And so we just need to preserve that. And so in that case, 2nt just needs to equal m times lambda. Does that work? That's
What-
between 1 and 2.
What is n one more time?
What is which one?
The one that appears in the equation?
N or m?
2n. N.
N is the index of refraction. Yay?
Thanks.
So that's between 1 and 2. Between 3 and 4, we have kind of opposite rules, right? Because these are already in phase by reflection. But 4 travels an extra distance of what compared to 3?
3t.
2t. Right? So 3 traveled here, 4 traveled here,
Oh.
here, right? So flip these rules if you're talking about 3 and 4. Yay? Questions, comments, concerns? Do we want to try and do an example of this? This ends at 55, is that true?
Yes.
Yeah.
Let's try and do an example. It's pretty fast. So, non-reflective coatings for a camera lens or a solar cell, right? You want as much light to get into your solar cell as possible. You don't want to reflect much. And so, we have more than we need. Air, silicon oxide, so n equals 1, n equals 1.45, and then some bare silicon, n is about 3.5, and those should be parallel even though they clearly aren't. So can you tell me by reflections, 1, is it 0 or 180?
180.
180, why?
N145 is greater than N1.
What about 2?
0?
180. Why?
Is it closed?
It's reflecting off of 3.5 and it's in 1.45. Okay? So let's figure out what thickness T will minimize reflective loss at 550 nanometers. So, are these in phase or out of phase by reflection?
Okay.
They're in phase. If we want to minimize loss, do we want someone here to see constructive interference or destructive interference? We want destructive, right? We don't want them to see any light coming back. We want it all to go in. Yeah? And so what's the extra travel distance 2 carries beyond 1? 2t. So does 2t need to be an integer or a half integer number of wavelengths? Half integer number of wavelengths. Yay? And so this is lambda over 2n, right? Lambda n is just lambda over n. I don't know where I put that word, but it's gone now. And so t needs to be lambda over 4n. And so lambda, we said, was 550 nanometers. Divided by 4 times, what n is it in when it's traveling that extra distance?
SIO.
SIO. And so that has an index of 1.45. And so this winds up being about 94.8 nanometers. So on top of your silicon, you want to deposit a thin layer of silicon oxide that has a thickness of about 95 nanometers in order to minimize the amount of reflection you get off of it. Similarly, this isn't, this is probably something that you would want to do for eyeglasses, right? You want people to be able to see your eyes through your glasses, and so you want to minimize the reflection of light off of your glasses so that they can see through to your eye. Well, you should do something similar. You can add some other layer if you want to minimize how much blue light gets through. There, rather than worrying about what gets reflected, you might want to maximize the reflection of blue light and minimize the passing of blue light. And so then you would pick 2 rays down here and try to get destructive interference of blue light wavelengths. I can tell by the packing of bags, I'm out of time. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your days, but not so much now. See you on Wednesday for your test. Remember that this coming weekend, to make it up to you, it's 1 hour shorter than normal because we spring forwards.
How lovely.
You're welcome. You'll hear my dull droning monotone an hour sooner than you otherwise would have.
How lovely.
I wanted to ask why
Let
the
me
second
take a
was 180 instead of 0. When I hear it,
Why 2 is?
yeah.
So here it refracts, so there's no phase change going from here to here. But here it's reflecting, it's in 1.45, it's reflecting off of 3.5. And so when it reflects, here it's gone an extra 180. You don't get any change for going through refraction, so from here to here it's the same. So from here to here, it went 180, didn't change at all from here, so it's 180. What's that? No, almost. If you send me an email, I'll bring it again on Wednesday. How are you?
Did a retake of quiz 1.
So the only reason earlier.
You can do that for every exam except for the very last one that you take right by
And then here at the bottom. What did you want that in the exam about, like, why was it?
a couple weeks later. If you got it to me, don't do it instead of studying for this exam.
Yeah, I was gonna do that this week.
Perfect. If you got it to me sometime next week, I'd be overjoyed.
Okay, that sounds good.
In my dull droning monotone, but still overjoyed.
Okay.
Bam!
How are you?
Do you
I'm
understand
well, how
why
are you?
we have to
Great.
be
I was actually wondering if this is the terminal.
I got all
Just
that.
to make sure.
Not the single slit diffraction stuff, but the thin film interference stuff, yeah.
Okay, so mainly it's going to be interference.
It's typical.
And mirrors, and, yeah.
Okay, perfect. Thank you.
You're welcome, have a great day.
You too.
Professor, would you please explain why we need half a wavelength? I got lost in that part.
So, do you want constructive or destructive interference up here?
Destructive, right? We want all that.
Destructive. So, they're in phase by reflections. The only way to bring them out of phase then is by the extra travel path that 2 takes. And so you want the extra travel path to correspond to half a wavelength so that they're now out of phase.
Oh, okay. Okay. Makes sense. That's why it's 1/2. Okay.
That's true. It's okay if I erase this stuff?
That's a quick question. So this one's also minimized, right?
This is if you want the reflection minimized,
Like,
which
is it possible-
maximizes the transmission.
Then what if like they ask to find like thickness
taking
instead of
classes again,
maximize?
Well, so if you would wanted this to maximize, then what you would do is you would
And then after that,
Wait, are you?
want this to be an integer number of wavelengths, so it's not divided by 2, it's just
I don't know, I
lambda.
have to take 121. though.
So you mean like the M we could do
That's the
1/2 as well?
120.
Yeah.
Say it again?
Next
And we could do
one.
1/2.
You're mechanical, right? Oh, that's
I'm confused with that. Like
for some reason
this
mechanical.
one's
you only
asking
have
for like
more
asking
of a-
minimize. That means like divide
If you
2.
want to minimize this reflection, they're in phase right now, you need to bring them out of phase, so the extra travel needs to be half a
Oh
wavelength.
yeah, I really like
Or if
that.
you ask for like maximize, you just
If you wanted to maximize here, then you don't want it to be half a wavelength, you want it to be a whole wavelength, so this isn't divided by 2.
So
this 2 isn't here. So this is 4n, it's 2n, right, divided by 2.
If you can.
Oh, okay, I see.
Which one?
Gotcha.
One.
Yeah.
Is it okay if I erase this now?
Oh, okay.
All right.
Yeah, maybe.
I have a
Next
question
semester
about
we'll have to
the
go back. How like 5G.
or if it's double slit.
Yes, sir.
I mean, I can take them.
I'm pretty sure I already asked you this, but you said,
Oh, shoot.
so you said